questions about anything and everything? Are the quiz solutions up there? I think so, right? Okay, what'd you have, Greg?
This week, could we do our quiz on Monday?
Can what?
Could we do our quiz on Monday instead of Friday for this week?
all right.
Possibility.
Yeah. All right, tell you what, we'll vote on it. Sounds fair? Keenan, count with me. If you want this Friday, one hand. He doesn't count. If you want it on Monday, one hand. By unanimous. It will be on Monday. Usually right about now. All right, any other questions about EMAG? We've done short dipole. We've done arbitrarily long dipole, didn't we?
We haven't started long dipole. We had a homework on it. We had a homework on
All
it. We
right,
posted
here's
it.
what I plan to do today. I'm going to first remind everybody about the short dipole as the building block. That's what we use to find the electric fields for the other straight wire antennas. Then after that, I'm going to put the I'll put the radiation resistance down for both the short dipole and half-wave dipole. These are wire antennas and the arbitrarily long dipole. You all with me, class? After that, I'm going to do the loop antenna. It'll be the small loop antenna. In other words, the perimeter is less than a tenth of a wavelength. Just like think of a straight wire antenna. For a short dipole, the length has to be less than a tenth of a wavelength. If it's a loop, just take the wire and bend it into a loop. The perimeter, 2 pi a, has to be less than a tenth of a wavelength. That's the basic constraints for anything that's short or small. Here's the characteristics for a short dipole. Now I'm going to tell you, this one you need to know from memory. Got it? So write it down. This not given. If you have a short dipole, it's a brand new marker, by the way. Can you all read that or not?
Yeah.
Short dipole. It means, first of all, the length of the antenna is less than lambda over 10. Now, that's an arbitrary figure, but it's pretty good. So that's the length of the wire L. Now, for an antenna like this, there's two ways to assume the current is distributed. The first is it's constant. So if you just take a look here, this is the z-axis in this direction. And you look at the magnitude of the current I of z, the first way they do it is assume it's a constant value, some I naught. This is actually never going to happen in the real world, but they use this as a building block. The reason it doesn't is the current has to go to 0 at the ends. If it doesn't, where's it going? You got 50 amps going up, then it's gone. Well, there has to be an explanation. Either there's a heavy capacitor there that's charging and discharging, or there's something else that you need to consider. Y'all with me, class? But we use this all the time as a building block. Using instead of L, it's DL. It's a differential length. Then if you come out a distance R, you're going to have an angle theta associated with this, and it's going to give rise to fields. The one I always remember is the E field, and we're going to assume we're in the far field. So I'll put down far field distance. So, by the way, what is the far field from a straight wire antenna? Does anybody remember? There is a distance where R has to be what? Greater than or equal to lambda over 2 pi for a straight wire antenna. Do you all remember that? Anybody? Do you remember it? Now that's something you're going to need to know. But in the near field stuff gets a little more complicated, and Wentworth kind of hand waves at this. He lets you take the magnetic vector potential, take the curl of it to get the H field, and then you're going to get a bunch of terms for the H field that somehow I didn't get when I did it, but you're going to get several terms for the H field, and you'll get 3 for the electric field. The only one you care about is the 1 over R variation. That's a propagating wave. The other field terms for both H and E that are functions of 1 over R squared and 1 over R cubed are related to near field energies. All right, so in the far field, the electric field is assumed in the theta direction, and it's given by, I don't know how many remember this, but it's J eta beta times the length times the value of I. In this case, we're assuming I is a constant. This is for a short dipole over 4 pi R. and r is the distance measured from the center of the dipole. The dipole is assumed at the origin at x, y, z equals 0. You all with me, class? Now, then it's multiplied by e to the minus j beta r. Now that's a phase constant, because as this thing's propagating, we are in the frequency domain, there's a phase change. In time, if we were in the time domain, there would be a time delay. But if we're in the frequency domain or in the phasor domain, there would be a phase change. And there's the very important sine of theta. And this is in the a theta direction. The units are volts per meter. So that's the electric field from a short dipole. The magnetic field from a short dipole in the far field. Do you remember what we did to get the magnetic field? We're talking about propagating waves, far field. Anybody, just in your own words, I'm not gonna.
Divided by the intrinsic.
That's right, you basically divide by the intrinsic impedance. That gives you the magnitude, then you gotta reorient it, right? Instead in the theta direction, the H field be in the phi direction because E cross H has to be direction of propagation. Does everybody understand me on this one? You guys good with this? All right. So for H theta, it's simply going to be get rid of eta, pardon me, eta. It's times beta L over 4 pi I naught over R e to the minus j beta R, and then it's going to be sine of theta in the a phi direction, and that would be amps per meter. I want to mention something. 99% of the time, whenever I do these problems, if it says short dipole, I grab this. That's because from that I can get the H field. From that I can get the power density. To me, it's very intuitive. Yeah.
So that sine angle stays theta, it doesn't change to phi?
No. That angle is, remember, E and H in magnitude will track each other at a given R. Remember, sine theta is, if you go straight up, what is it? What is the value of E straight up? I mean, at theta equals 0. Just take a look.
Positive.
Huh? What is the sine of 0? Let's try that.
Zero.
Sine of 0? 0, right? Nothing propagates straight up, nothing propagates straight down. That's where the direction occurs. Y'all, everything has to propagate in a way. I mean, propagation in the direction of current will always be 0 for a straight wire antenna, for far field. The maximum propagation or maximum strength field at a given distance r would be at what? At theta equal 90 degrees. If you looked at this is a very light marker, by the way. This may not be the best thing for me to do, but I'm going to. If you looked at a short dipole as such, and you wanted the radiation characteristics, now the power density on this is going to be, I'll put it up there. Remember, how would we get P-av if it's a propagating wave? Anyone. I mean, you can do it subtle ways. What would P-av be? In general, well, technically it's 1/2 the real part of E cross H conjugated, right? Do you remember that? Technically, though, the easy way to do it, if it's propagating, it's going to be, this would be in the AR direction, is going to be 1/2, and you can take the magnitude of the E field squared divided by eta in the AR direction, or you can take 1/2 and then take eta times the magnitude of the H field in the AR direction. Either one will get you. The H field might be easier because if I look at this and square it, magnitude squared, get rid of the J, then I got beta, which is 2 pi over lambda, times L, times I naught divided by 4 pi, so 2 pi by 4 pi is simply 1/2, right? Then you have,
Were you missing the intrinsic on that?
where? There's the intrinsic, right?
Oh,
H field,
right.
that's H field, right? Oh, I'm missing H field. That's right. So beta is 2 pi over lambda times L, so you're going to get 1/2 L over lambda, I naught over, and then e to the minus j beta r over r, sine squared. You might as well do this. I'll put it down right here. So the average power density is going to be equal to, now what I'm doing is, beta, I'm going to get rid of j. Beta is replaced by 2 pi. So P out here, I'm gonna do it this way, 1/2, then I'm gonna multiply it by eta, and then I'm gonna multiply it by h squared. But I'm gonna do this, I'm gonna say, now the h I'm gonna use, and I'm just taking magnitude, I don't care about the phase crap. Y'all with me, class? You with me? All right, so the beta is replaced by 2 pi over lambda. There's over 4 pi, so it's really going to be simply 1/2, and then by L, it would be L over lambda. So now I've taken care of that, that, and that. Then it's times I naught, got rid of that. I'm going to take, it's really 1 over r because the phase term goes away, and it's sine of theta in the a phi direction. Now, what I've done, well, I don't even need a phi. I'm trying to get rid of everything that could distract me, the n times the sine of theta. Yeah. Now I've got to take that right there and square it. Y'all follow me? You'll notice there's no eta in there. When I square it, I get what? Now I get 1/4, I'm going to put it here. And then I get L over lambda squared. You may want to write this down. Then I'm going to get I naught squared, and it's divided by 1 over r squared, and then sine squared of theta. And that would be in the AR direction, and that would be watts per meter squared. Whitworth has something like this, but he doesn't put, he's got a whole bunch of beta squared, stuff like that in there. This is, I think, easier. You can, the reason I have L over lambda, because now it's a short dipole, so if L is in terms of lambda, the lambda cancels. Y'all follow me? So if L is like 1/10 lambda, you get lambda over 10 divided by lambda, it's 1/10 squared is 1/100th. Y'all follow me? All right, it's easier to do it this way. You can replace eta, let me see if I can do this. So you can replace eta by 120 pi. Let's say I got 120 pi by 2 is 60 pi. 60 pi by 4 is 30 pi by 2 is 15, right? Pi. I'm trying to get rid of these terms. Then I still have to have L over lambda squared, I naught squared, 1 over r squared, and then sine squared of theta AR in watts per meter squared. That's probably an easier thing to remember for power density, but my go-to is always just get the electric field and work from there. And the rest I don't care about. Y'all with me, everyone? Okay, so that's the power density. Those are the electric fields. Now we have to talk about one other thing for the short dipole. We're going to do this for all the different antennas. We talked about the radiation resistance, how this antenna actually has a resistance that's associated with the radiated power. It has nothing to do with an actual loss in terms of heating of the copper or anything like that. It's the radiated power. It's the electrical, you might say, the transfer of electrical current power into photons of energy that are launched. You all with me, class? Now when you have, anytime you have a resistor, you get I squared, 1/2 I for AC, 1/2 I squared R would be the power consumption. Do you all agree with that? Average power. Well, the power that can be consumed can create heat. And I think most people they know that. I mean, you heat up, put a resistor and increase the voltage, more current, it'll just start getting warmer and warmer and warmer. You can specifically get to things where it would radiate light. That's photons, and it would be radiation, which you could argue is a type of high frequency. I mean, it's basically like heat. Some people think of it as infrared energy and stuff like this. Or you can get down to lower frequencies, and it could be electromagnetic energy that's radiated. So that's what we're really talking about. So for this thing, then we'll have a radiation resistance. So if I have a voltage here, some Vs, and I'm driving it, and I have my antenna here, the antenna can be modeled as some R radiation. Then there can be R losses that a loss effect. That's really the copper losses, and I'm going to tell you what that is. And there's also a reactive value that we don't cover much. It can be X antenna here. So the radiation resistance is associated with the radiated power. You with me? And the way this works is that let's assume there's a current flowing here. How would you calculate the current that flows if we knew what the actual radiation resistance was of the antenna that I'm about to put down, and the resistive losses, which we'll show you how to calculate, and the actual value of the reactive impedance? Anybody?
Few over see.
Yeah, it's simply take the voltage, whatever it is, if it's sinusoidal, peak value 10 volts, divided by all three of those in series. That's the current. You take the magnitude of the current, and once you have that, and I'll just put this Vs over, really, I can put R rad plus R loss plus JX antenna. Now, after that, what is R rad? Do you remember me doing this? We calculated total radiated power and equated it to the way we did this. We took total power radiated and we equated it to 1/2 I naught squared R rad, and that's how we calculated the radiate. We found P rad multiplied by 2 divided by I squared and calculated R rad. Do you remember doing that basically? Class? Andrew, do you remember it or not? I'm got to make sure everybody's at least on the same page as me. Do you remember what it was for a short dipole? For a short dipole, what was it? Wasn't it 80 pi squared L over lambda squared ohms? Now, here's the important thing. When you have a short dipole, you determine it's a short dipole. And when you want the total power radiated, now I'm gonna put one more thing down in a second. You need the current to get the total power radiated from the radiation resistance. You with me on this? Let's assume that we have the radiation resistance and we want the total power radiated. Well, P radiated, I just put it up there, I'll put it here, P rad is equal to 1/2 I naught squared, and that's a magnitude, times R rad. Now here's the progression of how I would do a problem. If, suppose I'm giving you a short dipole, and we'll do some of these, and it's connected to a source, and we'd have to know the copper losses and the reaction, or the reactance, but I'll get to that shortly. If we know the current, we can get P rad. Now, if we know the P rad, do you remember we calculated the directivity / gain for the antenna? So for a short dipole, the directivity is equal to simply 3/2 times the sine squared of theta. It has a maximum value of 3/2. Do you remember that? And it's multiplied by sine squared of theta. You with me? If we assume that there are no copper losses, so we're just going to say R loss is about 0, but I'll correct that in a bit. Then you can say, and I'm going to come over here, you can say that if I have this short dipole here, and I'm a distance R away, this is the angle, it's got a current I naught that we can determine, and that means that the actual power density here, now this is important, so if you want the actual average power density, right? Now we could, if we knew the current, we can go up here, we can get the power density, right? But I want to show you a shortcut that I always use. I always go for the gain. And if we assume the resistive losses are 0, then the gain, G, is the same thing as the directivity D. Can everybody follow me on this? If the losses are 0. Now the way you get the average power density, first you get the current. I mean, this is for most antennas. You get the current in the antenna, however it's limited. You have the current, You know the radiation resistance of the type of antenna you're using. So you know total power radiated, 1/2 times I naught squared R rad. You all with me? Now this is real important. I'm trying to make sure I convey this information. So to get the average power density at a given radius R for a given angle theta, we take the total power radiated and divide it by 4 pi R squared. I'm really big on this. What does that tell you? Well, that total power radiated is all the power that's launched, right? And if you go out any distance R away and put a sphere around there, all that power has to get through that sphere, right? So if you divide it by the area of a sphere, you have the isotropic power density at any radius R. Do y'all hear me? Right. Then you take that, and the thing that sharpens it is the gain. Now you just multiply it by the gain of the antenna, and now that's what the gain does. It's really the focusing or the enhancing ability. It can go down too, but the thing is the peak value will go up from an isotropic, and that's the key thing. That focuses it. It's like, you know, taking lenses with a candle, you can focus the actual light. That's the way I think of it. Or a parabolic, you know, a parabolic kind of reflecting mirror and put a candle in the center, it's all focused. You all with me? That's what that gain is. So that's the average power density. And for a short dipole, I can go ahead and put this in here, so it'd be P rad over 4 pi R squared. And then it's times 3/2. And then it's times sine squared of theta. Now that would be in the AR direction, watts per meter squared. Does everybody follow me on the reasoning? Now suppose, and this is the nice way to do things in my opinion. We got the radiation resistance, we know the gain. That's mainly, if you could buy a commercial antenna, that information will be given. It's usually given from plots, because the antenna has a different amount of radiation resistance and reactance versus frequency. The gain slightly changes, so you can interpret this from the plots. The gain function does change, and a lot of times you're looking at the gain versus different frequencies in terms of the angle theta, and you pick out the angle you want the actual value at. So you get this, and that is equal to 1/2 magnitude of E squared over eta, right? So now I can get the electric field. Take 2 times eta times this, and I can get the electric field magnitude. You all follow me? What you looking at?
Okay, I see that.
1/2 E squared over eta is the power density for a propagating wave, right?
That's the power
That's the total power radiated.
radiated something.
Okay, everybody with me?
So,
I'm showing you how I think about these things, and it makes things a lot easier. I got the electric field really quick, not you, Ken, not any of the people in the front. How would I get the H field? Just knowing it's a propagating wave. Anyone? Not you guys. So in the back. Greg.
divide by
Right, if it's in free space, 8 and 9. Does everybody agree? Just trying to make sure I'm clear. You with me? All right, now that's a short dipole, and I've really uncovered everything. Here's a couple other things I've got to add now. What about resistive losses? So now, if we want resistive losses, R loss, now make sure you write this down. You think of that short dipole as a solid chunk of wire that you want the losses in. And remember, now we're going to say the wire has a radius A and it has a length L. And we want the actual resistant losses between one end and another. So if we put a voltage here, we want to figure the current. What would limit current in terms of that being a straight piece of wire? Now, do you remember how you do this? You can say the actual DC resistance, RDC, would be equal to the length, right, divided by the conductivity. It's probably copper, but it could be something else. And it's divided by the area, which is pi A squared. And this would be in ohms, right? That would be if it had direct current and there was no frequency. Everybody? Now that may be the resistance you're going to use, but then you go ahead and you calculate the skin depth, which is 1 over the square root of pi f mu sigma. And if the skin depth is less than A, then the calculation you default to, let's say much less, because that's usually the case. Now you say that RAC, or R high frequency, that is the loss. This would be the loss if the skin depth was very long compared to the radius. Now you say this is going to actually be equal to the length divided by, then it would be like a perimeter right here. It would be 2 pi A. Remember, the perimeter would be 2 pi A, would be circumference or perimeter, times the thickness of a skin depth. Do you remember me doing this? How many do? With me? Do you remember it or not? If you don't worry about it. I just want to make sure I hammer this home. So that means it's this divided by 2 pi A times the skin depth times the copper conductivity, if it is copper. And that would be the losses, R loss in ohms. Now for a short dipole, R loss is usually of the order of the radiation resistance, which means you lose a lot of power just heating a thing. There's also a reactance for this that Whitmer's book doesn't show. But the short dipole has an impedance, like it's a piece of wire. It's got to have an inductance. Do you all agree with that? We could calculate the inductance. The problem is you need a partial inductance formula to do this correct. It's not just the internal. And his book doesn't get into that depth, and that's understandable. But then if you have that inductance, you could calculate the loss, or you could calculate the impedance. It would be J omega L. If you could figure out the L of that little segment. Do you all agree? And in fact, you can. It's not usually a relevant point to do it here because overall, the things that usually limit current in a short dipole are external. There's other things that are going to be dominant. Okay. Got power rating, got all the things for this short dipole. And so I'm just telling you right here, that's not an easy one to just pull out. I can give you a formula for it, but to justify it would be the internal inductance you'd have to calculate, which we did for a short wire. Then you have to calculate the external, and that's a partial inductance formula. Do you remember talking about that or not? The partial inductance formula is a little nasty. It's hard to explain without going into great detail. Some things that are well beyond the scope of this class. Okay, now we go to the next antenna. And that's going to be an arbitrarily long antenna. And this one doesn't have a closed form for a bunch of stuff, but it is good and useful because we're going to do a half-wave dipole next, after that. And then we'll get to the loop. Okay, now it's going to be a long dipole. What is long dipole? Well, L greater than lambda over 10. It's the inverse of the short. It doesn't say how long. For this one, we take a dipole. And let me just tell you one other thing about the short dipole that I didn't. I'm going to finish my thought on short dipole. I forgot to do this. So when you have a short dipole, the actual current, if it was truly a short dipole you were using, and these are used, then your current profile, if this was I as a function of Z, it would look like a triangle like this. This would be I of Z. Y'all follow me, class? What that effectively does is halves the radiation resistance. I don't want to go through all of it, but basically, for a real short dipole, R rad is going to be 40, not 80, pi squared. And then it's going to be L over lambda squared ohms. Now the reason is because, just look at this. It's got, if you think about it, half the current in a sense, right? It's exactly 1/2 the area of the, but there's a lot to this, and it will cause the radiation resistance to go down by 1/2. Without going through all the math on that one, it does. Just keep that in mind in the real world. We don't use that as a building block, though. We use the other one. So when you got a long dipole, and that's the length here, and you look at the profile of current. Now, I did tell you this. I know I told you this. I of z. It is not a triangle usually. It does something like this. This would be I of z, magnitude of I of z, versus the z-axis. I'm trying to make those symmetric, but they're not quite symmetric. You all with me? Now I'm always center feeding the dipole. You don't have to feed it there. You can feed it there. You can feed it at different points. It'll still develop this current pattern. I guarantee you. That current pattern. But the point that you feed it has a lot to do with the impedance. And it's best to feed it symmetrically, right at the center. Same length above as below the point you're feeding it. And this is just a differential gap, as small as possible. When you do that, you're going to get this current distribution, I of z, and this is in your book. And it's going to be some I naught, and then there's going to be a sign. And the way he does that, I believe he takes beta, and then it's times L over 2 minus the magnitude of z, is probably the best way to do it. Yeah, he's got it with z greater than 0 and less than 0. And he does put a phase term in there where he has, but that phase term, he's going to put a phase e to the j alpha. Don't worry about that crap. This is the main thing. All right, this is the thing you worry about right here. Now, the thing about this is, as the length changes, this current profile changes significantly. I want to just show you 2 examples. And because of that, the electric field you get in the far field, by the way, for this thing, in general, has to be calculated. It's not something that has a closed form. You all with me, class? Because that integral, I guess I could do it one time, but if you're out at distance r and you're in the far field, so let's assume we're at r greater than lambda over 2 pi. So we're in the far field, and we want the electric field. So the way that they generally say calculate it, and we could do this, it's going to be in terms of an integral, but we could say the differential electric field that would result from this, here's how we do it. We'd find the electric field associated with, let me leave that as R and use this purple marker now. I'm going to say I'm going to have current here. I'm going to have an I of z that's varying, and I'm going to go out distance, call it r prime away, still with the angle theta, and I'm going to say this has a differential length dz. So I'm going to go ahead now and say that the differential electric field from this differential chunk of current, just let me go through this one time, and I think I did part of this. I don't remember how far I got, but I want to just complete my thought here. So this differential electric field, look at this as the first dipole, the short dipole. Constant current, little, so it's going to be j eta beta over 4 pi. Then you're going to take your I of z, whatever form that takes, and then it's going to be times dz, because that's the differential length now. It's going to be divided by e to the minus j beta r over r. And this is actually going to be an r prime, like that purple one, times sine of theta. And this would be a theta volts per meter. Now it's a differential electric field, and I'm going to explain a few things. And you'll see why it's a pain. So for this differential electric field, I'm going to first try to take out everything that is a constant. We're going to assume theta, we're so far away that the difference in the value of theta for this r prime versus r is insignificant. So we can say this is going to be j eta, and then it's going to be beta over 4 pi. Now I can take the 1 over r prime equals 1 over r. So in magnitude, r is about equal to r prime. Now, I'm not talking about phase change, but I'm saying the distance from here to this point of observation is about the same as this one. You might as well just say we're a long way away and these are parallel rays. It's easier to think of it that way. So I can pull out 1 over r. I got the 4 pi. The sine of theta will be the same too. So sine of theta can come out in front. But here's where it gets interesting. And actually, I'll tell you what, I can leave the sine of theta in there. Now, if I think about this, I'm going to have sine of theta, and then I have e to the minus j beta r prime. And here's where it gets interesting. And I wish I drew this, made this a little taller. So this is r, and this is r prime, and we're at a height z. So this is 0, this is z. And we're assuming this angle is the same thing as this angle. Are y'all with me? This is like the antenna axis here. If you take the projection here, because this would form a right triangle, this distance right here, delta r, is going to actually be equal to r minus, and then it would be z times the cosine of theta. Just take a look at this for a moment. I want to see the distance, the difference in these two r's. They both go to the same point a long way away, so they're parallel rays. Make sure you see this, guys. This is kind of an important thing to see. If you look at the only difference is right here at the beginning. And that's the distance difference. So if this is a right triangle here, that's z, that's the hypotenuse. And I want to find this. Well, I know that what? Adjacent over hypotenuse is what? Cosine of the angle. And the cosine of the angle will go there. Now, this should make perfect sense. What's the difference in distance if we're at 90 degrees between these two? Take just a tilt, huh? It's nothing, right? They're exactly, take these two things, move them down to 90 degrees, they're both same length, right? But do it this way, and this one is longer by the actual value of z, correct? And sure enough, it works. When theta is 0, when we're looking straight up. Cosine is 1, it's r minus z would be delta r. So now I have to put that in the phase term. And that means I'm going to have e to the minus j beta r. That's measured from the center. And I have to put, it instead of r prime, I have really what? I have r minus z cosine theta. Then I'm going to have e to the j beta z cosine of theta. Can you all follow me on that? I know this isn't exactly the stuff you live for, but you have to at least appreciate the proof. You're engineers. You're going to have to do crap like this all your life. I mean, a lot of it too. All right. What does that mean to get E, the actual E field? Let me try to do it under here. Erase this. You know what? I didn't even put the I of Z in here, so I need to put that. Let me do it this way. There should be an I of Z here. So that means I have a differential electric field is going to be equal to J eta beta over 4 pi. Then I have I naught, and then it's going to be times the sine of beta over 2, beta times L over 2 minus magnitude of Z. Then it's going to be times the sine of theta times e to the minus j beta r, and then it's going to be times, I'm going to put it here, e to the j beta z cosine of theta. Now, I'm writing this down. I'm trying to just replace I of z in this one by the definition of I of z. You with me? Here I'm going to pull out everything that doesn't vary with z. We're assuming theta will not change significantly. R is a constant, basically. I mean, the distance R is, but there's a phase change here that you have to account for with the difference in length. So now I get the differential electric field, and you'll see why I'm doing this. There's going to be J eta beta I naught over 4 pi. Then I'm going to get sine theta. And then the fun begins. So, let's try it. Let me actually move this over here. I'm gonna get the differential electric field in the theta direction is J eta beta over 4 pi I naught sine of theta then it's going to be e to the minus j beta r. All those terms will not vary over the distance z. Then I have this stuff. I have the sine, you'll see why it's a pain in the butt now. Beta L over 2 minus the magnitude of z. And then it's going to be times e to the j beta z cosine of theta. And if you look for a moment at this, right here, the thing I'm boxing, that's the differential electric field, and there's a dz too that I need to put right there.
And your R as well in the denominator.
Yeah, over r. But if you look at this, I've got the differential. Now I need to integrate this thing to get the total electric field. This is my point. Integrate it from minus L over 2 to L over 2. And that means integrating this from minus L over 2 to L over 2. When you do that, here's what you get. And I'm going to do it over here. You're going to get the electric field. Tell me if he has this in his book. I don't know if he does. Is going to be equal to J eta beta I naught over 4 pi. And then I'm going to go ahead and put e to the minus j beta r over r. Those are functions of only r. I've got that and a sine theta. I think I need to take the sine theta in here because we're going to do it. And we're going to say, this is an integration in the back of the book, but this is a UdV integration, I believe, or VDU type thing. And you got to bring the sine theta. But at the end of the day, here's what's going to happen. He has the H field for his. This is the E field for me. If you look at this is kind of important. Whitmore's book has the H field. How would you get the H field magnitude if that's the E field class? Divide by 8 and reorient and put it in the A phi direction. Everybody agree with this? Now, here's my point. This right here is an angular function. It's only a function of angle, right? So typically what they do with a dipole antenna or anything like that, they're going to call that, well, this is called the electric field pattern or magnetic field pattern, but the power pattern would be that squared. Are you with me, class? In terms of angular function, I'm going to ask you something. That's the electric field. The power would be proportional to the E field squared. Do you agree with that, class? So this is where it gets hairy. By the way, that right there, that's the electric field. The power pattern would square everything. All this stuff, when you square it, is just going to have an I squared function over R squared. This is not of importance to what we're about to do. When you square that, you get something that you don't know what it looks like. It depends on beta L. You with me, class? Depends on that tremendously. And that pattern is called, that's the electric field or magnetic field pattern. The one in the book that Wentworth always goes for is the power pattern. Now, the way you get the normalized power pattern, you're going to have to bear with me on this one. If you think about a short dipole, the way we got the normalized power pattern, we took a look at its variation with angle. It was a sine squared, right? Sine squared has a peak value of 1, right? This one, that angular function, if you square the electric field, multiply by 1/2 and divide by eta, that angular function, and I'll call it f of theta, I'll call it small f of theta. That's cosine of beta L over 2 cosine of theta minus cosine of beta L over 2 divided by sine of theta. And that means, and this is the power pattern, he calls it f of theta, and it's equal to the magnitude of f, small f squared. This is the angle associated with power. Now, if you look at that, that means it's this squared. If you look at this function that I've got there, it's squared. It depends on the value of beta and L. It could have a maximum value of 1. And that would be when L is equal to lambda over 2. Just listen to me for a second. But it could have a value that goes to infinity. All right, I'm just saying this. It could have a value that goes to infinity as a max. Now the key is this sine of theta. You see this thing? When sine of theta goes to 0, it would be a theta equals 0, right? If at 0, this is not approaching 0 at the same rate, you have an infinite value. Do you follow me? You can't normalize that. I mean, it has no way, you can't get a p normal. You all with me on this class? Well, I guess there are ways, but normally what you want to do when you find the normalized power pattern for an arbitrarily long dipole, this you write down, p, and this would be normal, or p of n of theta. Now you say it is going to be a function of f of theta. That's the upper one over f max of theta. So now you have to find the maximum value of this function or the maximum value of this function. They are one and the same, aren't they, class? Because you're squaring this. Let me finish my thought. You all with me, class? How do you always find the maximum value of any function? I suggest you go here. With respect to theta. Take a derivative of the function with respect to theta and set it equal to 0. You with me, class? And here's the wild part. It depends on the beta L. Depends on the length in beta. Now, a half-wave dipole, the maximum you're going to get is at 90 degrees and in perfect normalization. But L over a full wavelength dipole, it doesn't have a solution. Not a closed form solution like that. You with me, class? I'm just trying to tell you this. So, in Whitworth's book, the reason I'm trying to make a point about this is simple. When you have an arbitrarily long dipole, the key, assuming it's a straight wire antenna, etc., you know this will be the actual angular variation. You know that. Beta is 2 pi over lambda. L, whatever the length is, will determine how this varies. And it can vary all over the place. You can get 2, 3, 4 different, they call them lobes in the power pattern. And it kind of drives you crazy. Now there are estimates, but the only one we really care about is going to be the half-wave dipole. Have you heard of a half-wave dipole before? So now I'm going to move to that part. I'm just showing you this. By the way, if you wanted to, if that was the electric field, just listen to me now. We can get the radiated power, right? What we do is take 1/2 the magnitude of that squared divided by eta. Now we have the power density, right? Then we integrate that over the spherical surface, right, of 4 pi r squared, but you'd have to say differential surface of r squared sine theta, d theta d phi, and integrate that, set that equal to power radiant. You can get it. But the integral is not closed form for a lot of different things. I mean, different conditions. Can you follow me in this class? I'm just telling you it's not as easy as, it's as cut and dry as the short dipole. It's not. So that's arbitrarily long. Now we're going to go to something that's important. And that's going to be a dipole that has a specific length, and we're even going to make it a little shorter for a reason. And that's going to be the half-wave dipole. This is very important. All right, now, if we have a half-wave dipole, so length equals lambda over 2. This is half-wave. This is the biggie. Real important. It's a straight wire antenna, and now the length itself is lambda over 2. So obviously, lambda is a critical factor in selecting the type of antenna you're going to use for the application. Now from that, the current for this one, this is important. When you look at I of z for this one, remember that's L over 2, so this is minus L over 2. This is L over 2. The current is going to look like this, roughly. And I'll have a peak value here, I naught. And the peak current will occur at the input point. And I of z will have the form I naught. And then it's going to be times the sine of beta times L over 2 minus magnitude of z. I'm going to modify this in a second, but you follow me? I'm just taking the definition of the current for an arbitrarily long dipole and putting it in there. And now, since it's a half-wave dipole, beta is equal to 2 pi over lambda, and L is equal to lambda over 2. That would be the current. Do you all follow me? I just tried to show you, I applied what beta is, 2 pi over lambda, and then I put the length in it is lambda over 2, got it divided by 2, it's lambda over 4. You all follow me? Now, here's the key thing. This is a sine function, right? The maximum the sine value can have is 1, isn't it, class? And here's how I know it's going to be at z equals 0, or at the origin, the feed point. Let z go to 0. You see how I have sine of pi over 2? You with me? That's the max. It'll go to 0 at the ends. When you let z equal L over 2, just look at this. When z is equal to the length over 2, the length is lambda over 2 divided by 2 is lambda over 4. Lambda over 4, the lambdas cancel, I get 2 pi divided by 4 pi, this is going to be pi over 2 then. So pi over 2 minus pi over 2 is 0, sine of 0 is 0. Correct, class? The next thing you get is the electric fields for these things. So remember the electric field pattern, f of theta is equal to cosine of beta L over 2 cosine of theta minus the cosine of beta L over 2 divided by the sine of theta. Does everybody remember that I had not capital F, small f. This is the electric field pattern. And this is put E/H pattern. You remember that, class? Now, replace, what is beta L? Let's do it this way. Well, beta is 2 pi over lambda, right? And length is lambda over 2, correct? So that means it's going to be simply pi, right? Then if I take pi over 2, what is the cosine of 90 degrees of cosine of pi over 2?
0.
It's 0. This goes away. And therefore, you're going to get the electric field angle. Please write this down. It's going to be cosine. And now it's going to be pi over 2 cosine of theta over the sine of theta. This one you can work with. So the electric field, now I'm calling that f of theta. The electric field will be J times 60. All right, then it's going to be times I naught. That would be the magnitude. Then you're going to get e to the minus j beta r over r. And that's the variation radially. Follow me? That e to the minus j beta r is the phase change as the thing propagates. And then it's going to be times this, that I call f of theta. So it's going to be cosine of pi over 2 times cosine of theta divided by sine theta. So that's e theta in the a theta direction. Guys, if I wanted to get the H field, what would I do? It's propagating, we're in the far field. Anyone? Divide by 80 naught and
Flip the feet.
reorient it, right? That's theta, it would be phi, right? How would you get the power density,
1/2 feet on square.
Hear me on this one. So we could go ahead and say P ab, right, would just be what? Magnitude of that squared. You all hear me? Let's go ahead and do it. So I'm going to have, if it's squared, I'm going to have 60 I naught. I'm going to just leave it like this, squaring it. Then it's going to be divided by r squared. Right, now I'm just taking e squared, then I'll divide by 80 naught in a second and put a 1/2. It's going to be divided by 2 eta naught. And then it's going to be this angular function cosine of pi over 2 cosine of theta divided by sine of theta squared. And this would be in the AR direction, and it would be watts per meter squared. I'm just showing you that what I've done is nothing more or less than squaring the E field divided by 2 eta naught. I want to show you what it goes to though. And I'll tell you what I'll give you. I mean, for a quiz or something, I'll give you the actual value of f, small f of theta, the angular variation. Maybe I'll give you the electric field and the power density for a half-wave dipole. All right, I mean the form of it. You all with me, class? Because this is still a little hairy. I mean, you haven't had enough time to be exposed to it and appreciate it. Now, if you replace, here's the way he has it in his book. And that should be the power density. Do you all agree with that? Now remember, the f of theta is this business squared. 8.80, page 458. Now that's important. The total radiated power, I'm going to tell you, I'm not going to ask you to do this for this one, but if you get the total power radiated, I have to multiply this thing by r squared times sine theta, d theta d phi, and integrate it over the spherical surface. The r squareds have canceled, but I got a 1 over sine squared. One of those sines cancels. The integral's a pain. Just level with it. Here's what happens at the end of the day. When all is said and done, we find, because to get the power radiated, what we really want is the radiation resistance, isn't it, class? So this is important. Write this down. For an exact, and write this word down, exact, and underline it, half-wave dipole, you're going to get the input impedance of the antenna. This is going to be the input impedance of an exactly 1/2, when L is exactly lambda over 2 long. You get the input impedance at 70, and he's going to have it 73.2 plus J 42.5 ohm, 460, and it's 8.85, and this is the impedance of the antenna. All right, now here's the thing to know. Please just listen. Remember, if we got the radiation resistance, this is the antenna, radiation resistance and the reactance. We have both here for an exact half-wave dipole. If I hook a voltage source to this antenna, I can figure out the current. Everything hinges on the current for power radiated. Once I have that, I can figure out the power radiated. 1/2 I naught squared times R rad. R rad would be the 73.2 ohm. Now, the directivity for this, and this is the one you got to write down, it's again a bit of a pain. You can do it, but we're not going to do it right now. We can get the directivity. It's one you're going to have to know. And of course, we find, by the way, the normalized power, I'm just going to tell you this. The normalized power is just that. The cosine pi over 2 cosine theta over sine theta squared. That is the normalized power. You don't have to figure it out because the peak value of that function is 1. Then you have to integrate that over the surface of a sphere, which is a bit of a pain. I'm just level. Yeah, I've done this kind of crap. And once you do it, you'll find this out. The directivity, and this will be for a half-wave dipole. D is a function of theta, assuming it's oriented in the z-axis at the origin, is going to be equal to 1.64, and then it's going to have that angular variation, which is going to be cosine of pi over 2 cosine of theta over the sine of theta squared. Now, that's the directivity. Here's the thing. If I have a half-wave dipole and I apply a voltage source, I have the radiation resistance, or I have the antenna resistance. You see this? I can get the current. Just take the voltage source, divide it, the magnitude, divide it by that. I got the current, right? Once I have the current, I have the total radiated power. That's 1/2 I naught squared times the radiation resistance. The radiation resistance is 73.2 ohms. Do you all see that? Now, once I have the radiated power, if I want the power density at any point r theta, I take total radiated power divided by 4 pi r squared. That's the isotropic power density would be there. Then multiply times this, we're assuming no loss, and now I have the enhancement factor. How much power density is out there, y'all hear me? To get the electric field, find that power density, set it equal to 1/2 times E squared over 8. I can figure out the electric field from that. Y'all with me, class? All right, guys. So, dates for the tests. Anybody? All right, that's it. 12 is, can you send me an email?
I'll send both.
I'm sorry, I'm so glad I got you. I'm worried about covering material and I didn't get to the loop antennas. But, and our quiz is Monday.